So about AC, do you remember where we stopped last time when we did AC? So for this topic, please use this the new slides that I have uploaded called Fundamentals of AC and Asynchronous Motors, AC asynchronous motors, because I made a lot of changes. So do you remember that we discussed last class how the voltage is not constant, it's varying as a sine wave, current is also varying, but there is a phase shift. This phi is the phase shift. Here they are in phase, here they are out of phase by 90 degrees because capacitor and the coil is an inductor, so they are out of phase in the other direction. So notice for the resistor they are absolutely in phase, the waveforms perfectly match, they both peak at the same point, trough at the same point. But for the capacitor, the current is peaking ahead of, it's actually lagging behind because the voltage has peaked earlier, but at a later point in time the current is peaking. That's because the capacitor has a different sign. So as you can see, the capacitor has a different impedance. So in AC we don't use resistance, instead we use this combined term called impedance, which takes into account the effects of the frequency and the capacitance. We will discuss the phasor diagram in detail later, but just notice one thing, impedance of a capacitor is negative, whereas for an inductor is positive. That is why in the capacitor, the current is lagging behind, it's coming at a later point in time, and in the inductor, the current peak is happening before the voltage peak. RMS values is just a mathematical thing, how we combine the various voltage values to get an overall value that we can use for our equations. We have a lot of squaring, so in AC we prefer using the RMS and not the average value. And this average has been done with the modulus of the voltage, because otherwise if you average this positive half and this negative half, it will get 0. So we take the modulus and then average them. And here we have the relationship V RMS equals V peak, the peak voltage related to 0 by root 2. Power factor also has been covered last time. It's just a side effect of the phase shift between the voltage and current. You have to take cos of that. It's kind of like work done. Then you have an angle between the force and the displacement. You take cos of the angle to get the work done. So work done is force times displacement times cos theta. Similar thing here, cos phi. And if you just multiply voltage and current, the RMS values, what we get, it's called apparent current, but it's not the real power being delivered. When you multiply cos phi, this whole thing is called power factor, you get the real power. And real power is what matters. It's actually power being transmitted. But apparent power, it is flowing on the wires, but it's kind of recirculating. It's flowing and coming back. And for ideal case where we want to utilize the given wire to the maximum extent possible, we try to have a high power factor, because when you have a high power factor, you are giving as much power as possible, and the maximum it can be is 1, because cos theta max is 1. When you have power factor of 1, it means voltage and current are perfectly in phase, and the current that you are carrying is absolutely useful to do work. But in reality, if you just have, let's say, the electrical power supply to mains, I connect an AC motor. What element does a motor have? It has resistances because of the armature, but it also has inductances. And inductances, it creates the phase shift, so you will have some power factor of 0.87, 0.86, 0.8 to 0.9 in that range. Sometimes it's worthwhile to do a power factor correction. You add a capacitor in parallel, which will shift the current in the other direction, so they can cancel out to get power factor close to 1. This is called power factor correction, and it's becoming more relevant today with the advent of electric vehicles. So the charging cable that is used from the charging station to the vehicle is DC, but before that internal conversion, it's good to have power factor of 1. Phasor diagrams. So we can go into detail about this, but it's going to take a lot of time. But in general, I will see if I can try to give a shorthand explanation. So this is something in the complex plane. Here is the real part, here is the imaginary part. And the voltage can be represented as a phasor, like so, which is rotating. It's literally a rotation in this plane. And the current will also be a phasor, which can either lag behind or lead the voltage, depending on whether we have inductors or capacitors. So this is the voltage, but if you look at the impedance, impedance is the AC equivalent of resistance. Impedance Z. So for a resistor, it's just R, and it's on the real plane because resistor does not create any phase shift. For an inductor, is J omega L, J because imaginary. For a capacitor, it is J by omega C in the negative. So it shifts downwards. So effectively what that gives is, you have the resistance, and let us say the inductance is dominating. J omega L minus J by omega C, and this is the effective impedance. And the angle we see here, that will be constant. This will be the phase shift phi, and you can use that to get power factor. So how familiar are you with phasor diagrams from FOE? Because it's covered there as well. So what do you know from FOE? Nothing. I mean, to truly scientifically, rigorously to describe it is going to take a bit more time. But from Drive's point of view, this is what we need. And even this might be a bit extra. We'll see. We'll find out later. So phasor diagrams are a useful way of representing AC voltages, current, and impedances. Three-phase AC. So why do we use three-phase? Why not just single phase like here? What disadvantage could be there? Because if you have three phases, it means you're having three live wires plus a neutral wire, and you have to transmit this over long distances. Why would you voluntarily try to take more wires? And you can do less.
It provides more uniform flux.
Yes. So in the motor, because a lot of the power being consumed is through in the form of motors, they are either in fans, conveyor belts, elevators. A lot of it is motors, and another major component is heating. And incandescent lighting used to be a deal, and those are resistive loads, so they don't care whether it's like that or like that. It doesn't matter for resistor. But still, you can see here, if you look at the overall average, the voltage is a bit more consistent than here. But today, the power demands have shifted. We have a lot of appliances which use DC, and they have their own internal power AC to DC converters. So this is not relevant for them. But for a motor, three-phase is fantastic because you have a much more consistent current delivery, which means you have consistent flux, which means the peaks and troughs of the torque is lower, so the torque is more consistent. So if you normally have torque like this, three phase you would be getting like this. So it's more consistent. And also in the same space you can get more power because instead of this, if you do an RMS of this, it will be lower compared to the overall RMS of these three. So they can get more power as well if you use three phase. That's why most powerful equipment, AC motors, they will have three phase power supply. So for example, if you go to a dentist and you have the dental chair, they have electric controls to move it up and down and change the angles. That uses three phase power. The elevator motor definitely uses three phase power. There is a phase shift between the three phases, how much do you think it is between any two phases? 120, because total is 360 and you want to be consistent. So if you look at the phasor diagram again, you will have one phase here, another phase there, and one phase here, 120 degrees between them, and they will all rotate together. The phase shifts will be consistent and they will rotate together. Very often we also use them in a 4-wire setup where we have 3 live wires, 3 phase wires, and 1 neutral wire. And a neutral wire is just a wire which is carrying the return current, but it doesn't have any voltage of its own, so it has potential of almost 0 volts. And with 3 phase, there's different ways to connect the same appliance. You can either have a star connection like this, where you have the 3 phases connected, and you have the neutral wire going out. Or you can have a delta where you rearrange the load such that you have only 3 endpoints to which you have to connect the live wires. And they have different properties, and we will see which one is going to make more power. But one thing to notice here, if you look at in the star connection, let's look at this specific load, is directly connected to this wire. So we can say that the current flowing through this load is the same as the current in this wire. But we cannot really comment about the voltage. We cannot comment about voltage in terms of between 2 wires. But we can comment based on the voltage between the live wire and the neutral wire. And these are 2 different voltages. So there's 2 different voltages in AC. You have a phase voltage and a line voltage. Phase versus line. In the phase voltage, you have it's from the live wire to the neutral wire. So if you look at the AC power socket, there's a big one here I could have shown you. You'll have some sign saying it's 230 volts slash 415 volts. What does this 415 mean? You always say 230. What is this 415? That 415 is the voltage difference between 2 live wires, because they have this phase shift of 120. It's not exactly double, it's a bit different. That's why here, so if you have V here between the line and the neutral, you will have √3 times of V. This by property, this 120 degree setup. Now let us look into more detail. Like I said, U line is √3 times of U phase. So, star or Y connection. The voltage across the load is phase voltage, which is U line by √3. Current is the same, I phase. Current flowing through a phase is the same as the current in the load. And when you look at the star and delta configurations, we talk about balanced loads, which means the loads are identical. So, all 3 of them react similarly to the same voltage being applied. Now let us look at this configuration. Imagine that this load is a purely resistive load. What would be the power across it? We have star. The resistance. UL. So what is the voltage across the resistor? Yes, but in terms of whether it's line or phase voltage.
Divided by √3.
It's phase voltage.
Phase voltage, exactly. And how can I get power dissipated by this resistor?
V square over R.
Yes, exactly.
U square over R.
P equals V square over R. In this case here, it is U phase squared by √3. Sorry, what √3? R. And if I convert it into the line voltage, it is UL squared by 3R. Right? Now let us look at the delta arrangement.
3 and not square root of 3?
Because it's a square. So it's UL by root 3 the whole square. U phase equals UL line voltage by root 3. Squaring both sides, U phase square equals UL square by 3. So here the power was UL square by 3R. Now we have the same resistor still here, just rearrange and it's the same power supply, just changing the connections. Now what is the voltage across the resistor? It's line voltage because you have one live wire here, another live wire there. So it's between two live wires. So P equals V square by R, which is UL square by R. So just by changing the configuration, I have triple the power. So that's why in soft start of the motors, we use star, it has less power, we have a slow and consistent starter without any jerks, sudden jerks. And once it's running at a decent speed, you can switch to delta, which will give the nominal power. So that's what I've described here as well, I think. This conversions, the total power is 3, is root 3 U line IPH cos theta. This is important. I did resistive loads to make you understand that delta can deliver more power, but it could be some other load as well, because for a motor you have a resistor and an inductor, so this power factor is involved. In general, the delta arrangement makes more power for the same load and the same power supply. We just saw that now. Because the current flowing is limited by the resistance, the armature resistance, not by the inductance. So even though there is an inductance, it does not affect the current that's flowing. So since a greater, stronger voltage is applied across the coil, more current is going to flow, which means more torque, meaning more power. So now let's start asynchronous motors. They are also called as induction motors, because here we don't have any separate field generating coils. We just have one stator coil that's going to generate a rotating field. So we have these stator coils, they are going to generate fields, and the field vector is going to rotate because the phasors, three phasors from three phase AC are rotating. So the effective magnetic field created is rotating, and this arrangement, this squirrel cage arrangement, this is the rotor. It has no power connected to it. There is no wires connected to it, and it doesn't take or give any power. But this is the core, this is the rotor, and because of this changing magnetic field, there are currents induced in this, because this arrangement wants to be in phase with the field, magnetic field, so it wants to rotate along with the magnetic field. And since the magnetic field is rotating, this also rotates. And you can see that it's because of the induced currents that the rotation is happening. That's why we call induction motor, made by Nikola Tesla. It's a very simple construction. We don't have any brushes or slip rings, which means there is no wear and tear effect on them. The motor will last longer. Self-starting in nature, widely used across the globe for simple applications like fans, blowers, pumps. Elevators probably not, because they need speed control. But maybe some cranes, simple cranes, stuff like that. RPM, rotational velocity, is not linked to frequency of input. This is why we call it asynchronous motor, because you can change the input frequency, but the RPM properties will not change. Like if you double the frequency, doesn't mean you have double the RPM. Doesn't change it. In this course, we will focus only on three-phase squirrel cage motors. There are more types of AC asynchronous motors. There's also single-phase motors, which just have one phase input and one neutral wire. We're not looking at that. We just look at three-phase motors. And for asynchronous, we focus on the squirrel cage type. So this is the core, which is rotating. But to strengthen the magnetic field, what we do is we have aluminum or steel sheets which can fit in these gaps made by the rods, and we fill this gap with many sheets,
Yeah.
and that strengthens the magnetic field and improves the torque being produced. The rods are skewed so that the self-starting properties are better. Squirrel cage with laminations, so the inside they're going to have many sheets which are laminated to prevent current from flowing between them, because
Any current losses.
yes, exactly, we want to avoid eddy current losses. And we have a housing which is holding everything together. Long lasting, like I mentioned before, we don't need any control equipment, it has a self-adjusting nature, but it's difficult to regulate the speed, exactly because of the self-adjusting nature. The RPM changes based on the torque demand. You can't use the electrical frequency to set that it should run at this RPM and take more current if needed, if more torque is required. You can do that only for synchronous motors. That's why electric vehicles use synchronous motors, because then you can control the RPM independent of the torque load. But the efficiency is lower compared to synchronous motors, which is also an advantage for synchronous. But usually we don't use synchronous unless necessary, because synchronous motors are more expensive and harder to control. So then the torque versus RPM graph. Here it's considered as locked rotor because it's at 0 RPM. And then we have the starting torque. This is the maximum torque you can do. It's called breakdown torque. If you try to put any more torque load, it will just stop. It won't rotate further, and then it will just make heat. But the nominal operating point, it's called full load, is here, and the slip is somewhat small. Slip is a new thing that's being introduced here. So we have this concept called slip. Slip is basically the difference in RPM between the AC field, the magnetic field made by the AC current, so magnetic field. So magnetic field is rotating at a fixed frequency. Let us say 50 Hz, which is what we get from AC mains. And the actual rotor. The rotor, if it rotates at 3000 RPM, it's going to match this 50 Hz, and there is zero slip. And at zero slip, there is no magnetic field difference between the field induced inside the rotor and the field made by the stator. There is no difference between them. They are perfectly in sync. And when this happens, there is zero force, meaning zero torque. That's why at the full operating speed, 100%, which is the maximum set by the frequency of the supply, you have absolutely zero torque. It's absolutely nothing. It's called no load RPM. That's why the nominal operating point is a bit to the left, where we actually have a non-zero torque. But why do you think we don't use the breakdown torque point? Because it's giving more power, right? Why not go there?
Maybe too much wear or unstable.
No. It's not about mechanical wear. It's something on the electrical side.
Heating.
Heating, exactly. So as slip increases, you have more heat. A very high amount of slip will have very high heat, which is why in these low RPM ranges, if your motor is somehow stuck there, because it is not able to overcome the, let's say the torque demand is here, let's say it was here. So in the beginning we had a high torque, so it was able to speed up, but once it reaches this point, it stays there. It's not able to proceed further because the torque made by the motor is dropping. If the motor continues to operate there, the slip is huge. It's like 90-95% slip. And in that case, it's going to make a lot of heat, which is very bad for the motor. It's damaging the coils, and very soon the coils will burn and the motor stops working. This is what we want to avoid. So the motors, electric motors, they are limited by their ability to dissipate heat. Because the coils are so tightly wound, they have a lot of limitations in how much heat they can dissipate. So if you use them at this high point. You can do that if you're doing it only for a short period of time. You can use it as peak current.
Can you use some kind of cooling system or something too?
Yes, you can have a fan, and if you have a very high power motor, you can do water cooling as well. So there are EV Formula One cars. They usually have water cooled motors.
Mm.
But water cooling adds complexity,
Yeah.
and you need this extra system for water cooling. And if something goes wrong, you have a water
Also
mixing with
electricity.
electricity. It's
Yeah.
bad. And this is what you can see is in the junction box. You will have the three phases of the motor, the stator coils, and you will have the freedom to rearrange them so that you can get either the star configuration where you have a single neutral point and each stator is connected to the live wire as a star arrangement, because let's take this phase U, it's getting the live connection and the other end is on neutral. Similarly with other phases, but here on one end we have one phase, and on the other end, we have another phase. This is the delta arrangement, and it's relatively easy to switch between these three arrangements in a junction box, which is why we have the soft start setup. Slides are uploaded.
Yeah, I just need that.
So some formula, N naught is considered the synchronous speed, where there is zero slip and the rotor is in perfect sync with the magnetic field's RPM. And this is a very important formula. The synchronous speed is 60 times FL, where FL is the line frequency, and this 60 is because it's going from seconds to minutes. This N naught is RPM, and P is the number of pole pairs. So this is a two-pole motor. This is one set. Like for each phase, you have one pole pair. So it's a two-pole, one-pole pair motor. But if the same phase has multiple pole pairs, then it slows the motor down, because P is in the denominator. So if you have applications where it's going to output low RPM, let us say for a fan, it's not going to run at 30,000 RPM, it's going to run at maybe 1000 or 500 RPM. You can increase the number of pole pairs to slow down the mechanical output and the synchronous speed. This is why if you look at windmills, their generators are also AC machines. They are synchronous, but this concept still applies. They have a very high number of pole pairs because on the mechanical side the turbine is rotating very slowly, like 100 RPM or so. But an electric motor, we need 50 Hz on the output side. That is limited because we want to supply to the grid. So we increase the number of pole pairs to decrease the gear ratio required. So this is the definition of slip, is N naught synchronous speed minus the current speed by synchronous speed. So it's like efficiency is from 0 to 1, or you can say it in terms of percentage. 3-phase power is 1 phase power times root 3. And this is not that important, we never consider the power of one phase. The Claus equation is super important. It gives the relationship between the torque at any operating point with the breakdown torque and slip. So a very common type of question that we see with asynchronous motors is the operating RPM is given, nominal, the breakdown RPM is given. We use that to get slip and we use that to get the torque. We will do such a question now. Like I said, it is possible to overload a motor. You can take it to the breakdown torque level, but the problem is that the heat produced is too much and you're not able to dissipate them over a long time. So this is why we use it on duty cycles, where you take it to high loads for short periods of time and then back to low loads again, or low load. But we will discuss duty cycles later. So here we have a simple question. Let's start.